Now we're going to take a look at a couple of problems for simplifying radical expressions. And these are both going to have radicals in them, and we're going to apply some of the beginning of properties of rational exponents, which come from section 7.2. And before we begin, I just want to remind you that we can convert between rational exponents and radical form quite easily. So if we had, say, the fifth root of x squared, that's equivalent to x to the 2. That's where the 2 comes in there, but it's over 5 for the fifth root. So the fifth root comes in the form of the 1/5 right there. So let's take a look at a couple of problems here. The first one is the fifth root of x to the 10th over y to the 5th. The first thing we're going to do is treat each one of these individually. So I'm going to write this quotient as the fifth root of x to the 10th and I'm going to put that over the fifth root of y to the 5th. We can do that because these are essentially fifth roots, and the fifth root applies to each of these individually according to our properties of exponents. So let's go ahead and go to that exponential form. So the top, or the numerator, becomes x to the 10 over 5 as the exponent. And that is all over y to the 5 over 5. So we see a couple of things here that become convenient for us, and that is the numerator becomes x squared, which essentially says that we can take the power of x, and if it's a multiple of the index of the radical, then we can just divide it straight in. So the numerator becomes x squared, and we now know also from the denominator that y to the power, where the power is the same as the index, cancels them out, and we're left with our answer, which is x squared over y. We're going to take a look at another one that has numbers in it instead of just variables, and we're going to start off with the sixth root of 8 times the sixth root of 16 over the sixth root of 2. Now you'll notice that none of these are perfect sixths. If you look on your little cheat sheet chart, you'll see that that is true. So what we want to do is realize that we can combine these and the denominator. So if you look at the properties of exponents, we could do 8 times 16 all over 2. That's because this is to the 1/6 and the 1/6 powers. We can use the property of exponents to say that these product can be combined, and the same thing is true with the quotient. So I did that all in one step. Just whenever the indices are the same, we can do that as long as you're talking multiplication or division. Now, we don't necessarily want to do 8 times 16. This would give you 128 over 2. Okay, and yeah, we could get there and it'd help, but let's go ahead and not do that and put everything in terms of base 2. Everything can be turned to base 2, so here we go. Let's do this. We get 2 cubed times 2 to the 4th and that's all over 2 to the 1st. Properties of exponents say that we add those exponents, so we're going to get 2 to the 7th over 2, which becomes, sorry, I forgot my indices here, just the 6th root of 2 to the 6th. We know that those cancel out, and we're left with just 2. So a couple of things about these problems. One, your answer is always going to end up something simple like this, okay? But resist the temptation to get too big. You might have seen that there's a 64 in here, and that the sixth root is indeed 4. But some of these numbers really might balloon up. And what I'd like you to realize is that if we stay in factors, and 8 going to 2 cubed is really breaking it down to its factors. When we break it down, things are going to fall right out. So this concludes our work with simplifying radical expressions.